All right, so now that we know what logarithmic form is, what we're going to do is look at the functions, logarithmic functions, and just see what their graphs look like so that we can kind of see how they behave with certain numbers. Let's go ahead and start by taking a look at this example. We're going to graph y equals the log base 2 of x. And in order to graph this, I'm going to make an x and y chart here and plug in some values that we know can work, and it might be easiest if I rewrote this in exponential form, which is the form that we're used to seeing. If I did that, I would have 2 to the y equals x. And so what I'm going to do is start by plugging in values of y that I know will give me numbers for x. So for example, I'm going to plug in a y value of 0. Because I know that 2 to the 0 is going to give me an x value of 1. Well, that's going to be a point that is right here on my graph at 1, 0. Well, let's plug in other numbers. I know that if I plug in a y value of 1, that 2 to the first is 2. So that's going to give me a point at the point 2, 1, which is here. I already had a point here. If I plug in a y value of 2, well, then 2 squared is 4. And so I'm going to go over 4 and up 2, which is right here. And I can continue this. I can even go 3 and 8 if I wanted to, which would give me a point at 3 and 8. Now, let's just take a look and see what happens when I plug in negative values for y. If I plug in a negative y value, like negative 1, well, that's 2 to the negative first. 2 to the negative first is the same thing as 1 over 2 to the first, which is 1/2. And so that's going to give me a value of 1/2, which is about right here. It's going to be over 1/2 and down 1. If I plug in, let's just plug in a bigger number. Let's say negative 3. So that would be 2 to the negative third power, which is 1 over 2 to the third power, which is 1 over 8. And so that's going to be a point at 1/8, comma, negative 3. So 1/8 is just going to be barely to the right, and then down 3, which is going to be about right here. You can see what's happening here is we have a graph that when we graph it, it's going to look something like this. That should look familiar to you, especially if you turn your head sideways, because it's the inverse of a function that we've already done. Remember, when we find inverses of functions, we switch the x and the y around. So for example, if I take a look at this function, which is the exact same thing as the function we started with, y equals the log base 2 of x, and I switch the x and the y around, I will have y equals base 2 to the x power. Well, this is a function that we can graph and have graphed. It's just like 1 times 2 to the x, which if we were to graph this, let me go ahead and graph this in a different color. If I were to graph this function, the starting value is at 1. And every time I move to the right, this is an exponential function, it doubles. So it's going to be at 2, and then at 4, and then at 8. And you can see here, even if I go backwards, I'm cutting it in half. You can see here that it's going to be a function that looks like this. And that makes sense because if you remember correctly, when we find the inverses of each other, of different things, they are reflected over this line where y equals x, and that's exactly what's happening here. Logarithmic functions are inverses of exponential functions. That's going to be key to what we're going to be talking about in a few days when we're solving exponential functions. What is the domain? Now remember, we're talking about the original graph that's in red. The domain is all the x values that are greater than 0. So it's greater than 0. And so it's not equal to 0 because there's like a vertical asymptote here that it approaches but it doesn't touch. Just like there's a horizontal asymptote in the blue function that it approaches and never touches. The range is the y values, so it goes forever down and it goes forever up. And so the y values are all real numbers. And so there's a key here. The base here is 2, and I want you to see how these graphs line up with a base of 2. Anyway, we're going to go through and we're going to be able to graph different logarithmic functions and be able to figure out if the base is a certain number, how does that behave on a graph. So let's take a look at the next equation. The next equation is the same thing except the base is 6. And so if I start this equation, I can plug in x, y values again, and I can plug in numbers that I know, like this is the same thing. Let me do this again. 6 to the y equals x. If I plug in a y value of 0, then 6 to the 0 is 1. And that point is still on the graph. But then my next point, if I plug in a 1, it's going to be 6 to the first power, gives me my x value, which is 6. Well, that's going to be the point 6, 1. And I can find other values here, but what's going to happen is same basic shape, except it's going to be a little bit sharper of a turn. I'm still going to have an asymptote here that's vertical along the y-intercept, and it's going to go off to the right. Here is what I want you to see, though, and that is that I always have the point at 0, 1. It doesn't matter what the base is going to be. Anytime I raise something to the 0 power, I'm going to get an x value that is 1. So that point will always be on the graph. The next point that will be on the graph has to do with the base. Here I went over 6 and up 1 because the base was 6. 6 to the first is 1. The last equation I had a 2 here, and my next point was not at 6, 1, but at 2, 1. And so that's how you can look at the base and be able to determine what the shape looks like. What is the inverse of this function? Well, if I switch the x and the y around, it's going to be 6 to the x is equal to y. And so the domain here, the domain is that the x values have to be greater than 0, and the range are the y values, and the y values are equal to all real numbers. Let's move on and take a look at a different equation. So what happens when we add something inside the parentheses here? So like before, I'm going to go ahead and make an x and y chart here. But as you know, in the past, let's do this too. Let's rewrite it as 3 to the y equals x plus 3. And so now it's an exponential form. And so now I want to graph this equation. And so in the past, we always plugged in a 0 for y. And so if I do that here, if I plug in a 0 for y, then that 3 to the 0 is going to be 1, and I need x plus 3 is going to have to give me a value of 1. And so if I subtract 3 from both sides, I'll have that x is equal to negative 2. So in the past, we always had a point that was 1, 0. Well, this is not 1, 0. This is negative 2, 0. Well, to go from 1, 0 to negative 2, 0, that means I had to move over to the left 3 spaces. And so what did the x plus 3 do to my graph? Well, let me get back there. It took the first point and it moved it 3 spaces to the right. And it's going to take every point and move it 3 spaces to the right. So this x plus 3 actually shifted the whole graph 3 units to the left. So I can actually start 1, 2, 3 units to the left. This is my asymptote where the line approaches but never touches. Then I could think of this just like I would my other graphs. It's going to have a point at 1, 0. So if this is my origin here, my 1, 0 is actually at negative 2, 0, which is what I have here. The base is 3, so normally I would go from my origin, which is this point, and I would go over 1, 2, 3, and up 1, and I'm going to do the same thing here. As a matter of fact, if I plug in a 0 for x, I would get a 1 for y. We should probably make sure that that point works. If I plug in a 1 here for this y, 3 to the first is 3. So 3 equals some x plus 3, and if I subtract 3 from both sides, I know that x is 0. So I'm going to have the same graph, except I'm slid 3 units to the right. So when I have a number that's in parentheses here, like the x plus 3, it moves it left and right opposite of what you would think. The domain values are that the x values have to be greater than 3, negative 3, because this is negative 3, and my range values are that the y values are all real numbers. What's the inverse of this function? Well, I'm going to take this function here. I'm going to switch the x and the y around. So I will have not over on this side x plus 3, but y plus 3 equals 3, not to the x, or not to the y, but to the x. And if I solve this equation for y, I will have y equals 3 to the x minus 3. And again, if I were to graph this equation, I would shift this down 3 units. So I'm shifting my exponential function graph down 3 units, and the base, the beginning number is 1, which is here, and then I'm going to go up by 3, and so it's going to look like this, and you can tell that those are reflections of each other, which are inverses of each other. They're reflections over this line here. All right, let's move on and take a look at this fourth graph, which looks like this. Now, not only are we moving things left and right, but what do you think is going to happen with the plus 3? And if you said that that means the graph is going to be moved up 3 units, you're exactly correct. Let me go ahead and graph this, and then we can just plug in points to see if we're correct. The x minus 2 means that I'm going to shift my graph 2 units to the right, which means my asymptote is going to be right here along this vertical axis. And my origin is going to be moved 3 units up. So this point right here is kind of like my 0, 0 point. But the base is 4. So because the base is 4, I'm always going to have a point at 1, 0. But it's really not 1, 0 because my point of reference is this new origin. So that 1, 0 is actually this point here. That's the point 3, 3. So I think the point 3, 3 is on the graph. And then because the base here is 4, I'm going to go from my origin, my new origin, and I'm going to go over 1, 2, 3, 4 units and up 1, and I'm going to have another point here. So it's going to look something like this. If I want to check to make sure that this is right, this is the point 6, 4. And so just to make sure I'm doing this right, I'm going to plug in I'm going to rewrite this first. I can subtract 3 over to this side, so it's y minus 3 equals the log base 4 of x minus 2. And so I can rewrite it as 4 to the y minus 3 power equals x minus 2. So let's just plug in a 4 for y and see if I get a 6 for x. If y is 4, then this is going to be 4 to the 4 minus 3, which is just 4. That equals x minus 2. And if I add 2 to both sides, x does indeed give me 6. And so x equals 6, and this is my graph. The domain values are all the x values that are greater than 2, and the range values are all the y values that are all real numbers. What's my inverse function? Well, what I'm going to do is take this function here and switch my x and y around, so it's going to look like this. Instead of x minus 2, it's y minus 2 equals 4 to the x minus 3rd power. And I'm going to add 2 to both sides, so it will get the y by itself. I'll have 4 to the x minus 3 power plus 2. And as we talked about before, the x plus 3 is going to shift it 3 units to the right and then 2 units down, or 2 units up. And then I would have the image reflected over that same line. Okay, so we don't have a whole lot of time here. And so if there's a 2x here in front, I'm going to leave that one up well, we'll talk about this one in class, if there's a 2x out in front for the sake of time. All right, so I won't leave it totally up to you. If I rewrite this, it's 2 to the y equals 2x, and you can make an x and y chart here. One of the numbers you can plug in is 0, and if I have 2 to the 0, that's going to equal 1 equals 2x, which means x is going to be a half. So instead of a point at 1, 0, I'm going to be at a half 0. Well, how did the 2x affect that point? The other thing that I normally plug in is a 1 for y, and if I plug in a 1 for y, it's going to be 2 to the 1st equals 2x, which means if I divide by 2, x is 1, which means another point is the point 1, 1 on the graph. And it's going to be a graph that looks something like this, where those 2 points are on the graph. And so how do the 2 affect the graph? The other thing that I want you to consider is what is the inverse? We'll see.